Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected. From the secrets of the cosmos to the marvels of everyday life, each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Okay, let's unpack this. Imagine we told you there's a world right here on Earth, bigger than Mars, filled with creatures, straight out of science fiction, and we've barely scratched its surface. You might think we're talking about a newly discovered exoplanet, right? A distant moon, maybe?
Yeah, somewhere far, far away.
But no, we're talking about Earth's own deep oceans, hands down, probably the most alien place we know.
It really is.
It's truly astonishing when you consider that we actually have better maps of the surface of Mars than we do of our own ocean floor. I mean, think about that for a second.
It's pretty wild.
We're literally more familiar with a planet millions of miles away than with, most of our own home. So our mission for this deep dive is to explore the incredible sources you've shared, uncovering the most mind-bending facts about this unexplored realm and its bizarre inhabitants. We'll try to make the complex accessible and, honestly, just absolutely fascinating.
And what's truly fascinating here, beyond just the sheer scale of it all, is that this isn't simply about, mapping new territory or finding new species. It's really about challenging our fundamental understanding of life itself.
How so?
Well, the conditions down there, we're talking crushing pressure, perpetual darkness, extreme temperatures, sometimes weird chemistry, often a complete lack of what we'd call normal food sources. It's forced evolution to get incredibly creative, like really radical stuff.
Right.
It's a relentless re-engineering of life's basic building blocks in ways that they defy our surface world logic. We're going to dive into organisms that genuinely seem more like science fiction than, biological reality. And ultimately, we're exploring why this matters to you, the listener. Not just as scientific curiosity, though it's definitely that.
Oh, for sure.
But for understanding the very potential and resilience of life itself, both here on Earth and, importantly, for thinking about what might be possible elsewhere, out there in the universe.
That's a powerful way to frame it. So when we say unexplored, how much are we really talking about? Because my mind immediately goes to, vague numbers, but I get the feeling the reality here is far more staggering. How much of this alien world is still just completely unknown?
Well, the numbers alone are humbling, to say the least. The ocean covers over 70% of Earth's surface, right?
Raid the blue planet.
Exactly. Yet the stark truth is, we have explored less than 5% of it. Less than 5%.
Wow.
To put that into perspective, imagine knowing only the porch and maybe the front yard of your house, while the entire rest of the mansion, filled with secret rooms and hidden passages, remains completely untouched.
That's a great analogy.
We're basically in that situation with our own planet. The ocean's average depth is approximately 12,100 feet. That's about 3,688 meters. But then you get places like the Challenger Deep.
In the Mariana Trench.
Precisely. It plunges down to an incredible 36,200 feet. That's over 11,000 meters deep.
Okay, that's hard to even picture.
Right. So to really grasp that depth, try this. If you were to place Mount Everest, the tallest mountain on land, at the bottom of the Challenger Deep, its peak would still be more than a mile underwater.
A mile of water still above Everest's peak.
Yeah, a mile. It's not just deep. It's an entire hidden world layered beneath the one we know.
That's just mind-boggling, a true testament to the scale. So, okay, that remaining 95% we haven't explored, what kind of immense unknown features could be hiding there? It can't just be empty water, can it?
No, not at all. Not empty space.
Huh.
I mean, if we connect this to the bigger picture, it's astonishing to consider. We have detailed maps of only about 20% of the seafloor. And even those maps, they often lack the resolution to reveal smaller features, intricate ecosystems.
So even the mapped parts aren't fully understood.
Exactly. That remaining 80% represents an area larger than the entire surface of Mars.
Yeah.
And it's filled with geological wonders, unexplored habitats. We're talking vast, submerged mountain ranges, deep-sea canyons that dwarf anything on land.
Bigger than the Grand Canyon.
Potentially, yes. Abyssal plains stretching for thousands of miles. Potential hydrothermal vent fields that no human eye, no camera has ever directly observed. Each of these unexplored regions potentially harbors unique ecosystems, species that have evolved in total isolation for millions of years, just waiting to be discovered.
Okay, break that down a bit. What kind of specific features are we talking about?
Well, Take the mid-ocean ridges, for example. These are these immense underwater mountain chains. They stretch for an incredible 65,000 kilometers around the globe.
65,000 kilometers.
Yeah, that's longer than all the continental mountain ranges combined. Yet vast stretches of them remain virtually unexplored. They're critical because they are like the engine rooms of our planet. It's where new ocean floor is constantly being created through volcanic activity.
Underwater volcanoes, basically.
Essentially, yeah. And this process creates incredibly unique environments. The discovery of hydrothermal vents along these ridges back in 1977,
Yep.
that was a monumental moment in science. Truly paradigm shifting.
Why was it so huge?
Because it completely revolutionized our understanding of life. It revealed entire ecosystems based not on sunlight, but on chemosynthesis, using chemical energy. It fundamentally changed our ideas about how and where life can exist. Before that, we thought everything ultimately relied on the sun.
So these are underwater volcanoes creating entire new worlds of life powered by chemicals. That's incredible. What about other geological features? Are there like regular mountains down there too?
Absolutely. Then there are seamounts. These are basically underwater mountains that rise dramatically from the ocean floor. They don't usually break the surface.
Okay.
They number in the tens of thousands globally.
Yeah.
Yet fewer than 1% have ever been properly explored. Imagine that. Fewer than 1%.
That's an incredible number of unknowns.
And each seamount creates its own unique environment. Its sheer mass affects currents, water pressure, the chemical composition of the water around.
So each one is like an island.
Exactly. Each one is a potential isolated island, potentially harboring endemic species creatures found nowhere else on Earth. They might even serve as stepping stones for deep-sea species, creating these chains of evolution and migration across vast ocean basins that we're only just beginning to even guess at. The potential for discovery in these unseen worlds is it's literally boundless.
That immense scale and hidden geography is truly humbling. But what's really astonishing to me is what life endures to simply exist in such a place. So let's maybe pivot from the unknown territories to the raw physics of survival down there.
Yeah.
What would instantly kill most of us, these creatures call home, it's like stepping onto a different planet with its own set of rules, its own kind of alien physics.
Precisely. That's a great way to put it. Life in the deep ocean has to contend with conditions so extreme they would instantly kill most surface-dwelling organisms. It's a masterclass in biological ingenuity, really. Let's start with the pressure, the crushing pressure. At depths of around 4,000 meters, that's about, 13,000 feet?
Oh.
The pressure reaches an astonishing 400 times atmospheric pressure at sea level. 400 times.
How can you even visualize that?
Well, try this. To put that in a way you can really feel, that's equivalent to having the weight of 50 jumbo jets pressing down on every single square meter you occupy.
50 jumbo jets on 1 square meter.
Yep. If you were down there without protection, you'd be instantly flattened, like a pancake flat.
And yet, these creatures are not only surviving but thriving. How do they not get squashed like tin cans?
It's truly remarkable. Deep-sea organisms have evolved these extraordinary adaptations. For one, many lack gas-filled organs, like the swim bladders fish near the surface have. Those would simply collapse.
Right, gas compresses.
Exactly.
Yeah.
So instead, they often rely on liquid-filled body cavities, and liquids are largely incompressible. But it goes deeper than that, down to the molecular level. Their very proteins, the workhorses of every cell, have evolved specialized structures. Think of them having extra strong internal supports, like in a building designed for earthquakes, but for pressure.
So their molecules are built differently.
Fundamentally different in some cases. And here's where it gets truly wild. Some deep-sea fish have proteins that actually require high pressure to function properly.
Wait, they need the pressure.
They need it. They would denature, essentially unfold and break down, and the fish would die if brought to the surface too quickly. Their biology is tuned to that extreme.
Wow.
It raises this important question. How deeply integrated are these organisms with their environment? Are they truly alien, even at a molecular level, dependent on conditions lethal to us?
That's a profound thought that our world would actively kill them. So pressure is one huge extreme.
Sure.
What else defines these depths? Because I imagine it's pretty dark down there.
Indeed. Then there's the perpetual darkness.
Mm-hmm.
Below about 1,000 meters, maybe 3,300 feet, sunlight completely vanishes.
Yeah.
Gone. It creates a world of eternal night.
Total blackness.
Total blackness. And this vast dark expanse is broken only by the ethereal, sometimes mesmerizing glow of bioluminescence, living light.
Bioluminescence, right. Light made by creatures.
Exactly. It's estimated that up to 80% of deep-sea creatures produce their own light through complex chemical reactions. They usually involve specialized proteins called luciferin and luciferase enzymes. They're like nature's own little light-producing factories.
So it's not just a lucky accident, it's an active process. But
Yeah.
why? Why produce light if there's no sun anyway? What's its purpose down there?
Oh, it serves multiple critical purposes in a world without any other light source. This biological light can act like a living lure, dangling in front of the mouth to attract unsuspecting prey right to them.
Like the anglerfish.
The classic example, yes. It's also used for communication, especially finding potential mates, like a silent flashing language in the dark, helping them find each other in this vast, sparsely populated world.
Makes sense.
It can also confuse predators. Imagine a sudden burst of blinding light when something tries to attack. Or it can simply illuminate the immediate surroundings for a brief moment, helping them search for food. It's a world where light is a tool, a language, a weapon, and a lure, a completely reimagined sensory landscape.
Fascinating. Okay, pressure, darkness. What about temperature? Is it just freezing cold?
Well, mostly, yes. And finally, let's talk about temperature. The typical temperature in the vast majority of the deep ocean hovers just above freezing, usually between 2 to 4 degrees Celsius. That's about 35 to 39 Fahrenheit. It's an intensely cold environment for the most part.
Okay, frigid.
But this isn't uniform. Near those hydrothermal vents we mentioned earlier, temperatures can soar to over 400 degrees Celsius.
400 C, that's hotter than boiling water, hotter than an oven.
Oh yeah, way hotter, 752 Fahrenheit. It creates these dramatic temperature gradients over incredibly short distances. Sometimes just a few feet apart, you go from near freezing to scalding hot.
How does anything live with that? Imagine having to adapt to both freezing and boiling temperatures in your daily life, practically side by side.
Right. Life near these vents has evolved incredible solutions. They have antifreeze proteins, like tiny molecular barriers preventing ice crystals from forming in their bodies in the cold parts. And then they have heat shock proteins, which act like emergency repair crews, stopping other vital proteins from unfolding and breaking down in the scalding heat.
Wow.
It's just a testament to evolution's incredible, almost unbelievable adaptability. Life finds a way even in the most seemingly impossible conditions.
All right, with those incredible, frankly brutal conditions in mind, what does life actually look like down there? Because I can't really imagine anything we see on the surface surviving, let alone thriving. Prepare yourselves, folks, because the creatures already discovered in the deep ocean read like a catalog of alien life forms, each more extraordinary than the last. This is where it gets really interesting.
Indeed, the diversity and the bizarre adaptations are just astounding. Let's start with the vampire squid, Vampirotethys infernalis.
Sounds ominous.
Its name literally means vampire squid from hell. And it's kind of fitting, given its appearance and where it lives. It inhabits the oxygen minimum zones of the deep ocean areas where oxygen levels are so low that most animals just can't survive.
So it lives where others suffocate.
Pretty much. And this creature is a living fossil. It's virtually unchanged for millions of years, possessing features of both squids and octopi. Very unique lineage.
What does it do that's so weird?
Well, when threatened, it performs this really dramatic defense. It turns itself inside out. It inverts its webbed arms over its body, revealing rows of dark, spiny projections called cirri. It transforms into this kind of spiky, unappetizing ball.
Turns itself into a spiky cape. That's amazing.
It is. And its eyes, its large, luminous eyes, are proportionally the largest of any animal on Earth relative to its body size. Perfectly adapted to detect the faintest traces of bioluminescent light in the absolute darkness of its home.
So it's a creature that basically turns itself into a spiky ball to scare off predators, all while seeing better than almost anything else down there.
Incredible. What about finding a mate in such a vast, dark world? That must be a huge challenge.
It leads to some of the most outlandish solutions imaginable. Take the anglerfish. This creature represents perhaps the most, alien reproductive strategy known to science.
I think I've heard about this. It's weird, right?
Oh, it's beyond weird. In many species, the male is tiny, like really tiny, little more than a set of eyes and reproductive organs, basically swimming tests.
Okay.
When he finds a much, much larger female, he latches onto her, bites into her flesh. And over time, his tissues actually merge completely with the females. They share circulatory systems, digestive systems, everything.
Wait, they fuse together?
Completely fuse. He becomes, quite literally, a permanent, living, sperm-producing organ attached to her body.
And some females even carry multiple males attached to their bodies, creating these bizarre, chimeric organisms that truly challenge our whole understanding of what an individual is in biology.
So she just collects them.
Seems like it. It's completely unique and, you have to admit, highly efficient solution to finding a mate in a vast, dark, sparsely populated world where just bumping into someone else is incredibly rare.
Okay, that's definitely a bizarre symbiotic relationship right there, a permanent living attachment. And what about their other senses? How do they, navigate and hunt besides the lure?
Well, speaking of senses, another marvel is the barrel eye fish, Macropina microstoma.
Hmm.
This fish, okay, get this, it has a transparent head.
A transparent head, like you can see inside.
You can see right through it. It's filled with this clear fluid, and through this transparent dome, its tubular eyes, they look like little barrels can rotate. They can look straight up to spot prey silhouetted against the faint, faint light filtering down from way above, or maybe the bioluminescence of other creatures.
So its eyes are inside the clear head.
Yes, and these remarkable, almost periscope-like organs can even move independently. The transparent head acts as a protective shield, safeguarding its delicate eyes while allowing maximum light sensitivity in the pitch-black environment. Imagine having a transparent skull and eyes that swivel around like living periscopes, constantly scanning the gloom above you.
Nature is just weirder than fiction.
Oh, yeah.
Okay, what else?
Then there's the gulper eel, sometimes called the pelican eel. Its feeding adaptation is truly incredible. It has this enormous mouth, makes up about a quarter of its body length, maybe more, and it can unhinge its massive jaws to swallow prey much, much larger than itself.
It's like snakes on land.
Kind of like that, but maybe even more extreme. Its stomach is incredibly elastic, stretching to accommodate meals that might have to sustain it for months in the food-scarce deep sea. Its body is essentially, well, it's like a living bag with a tail and a massive mouth, perfectly optimized for opportunistic feeding in an environment where the next meal might literally be months away. Every single calorie counts down there.
So it's essentially a giant, stretchy vacuum cleaner optimized for rare but enormous meals. That sounds like a brilliant, if maybe slightly grotesque, solution. But we've talked about weird and wonderful. What about just plain big? Is there a trend towards gigantism in the deep, like things getting way bigger down there?
Absolutely. We definitely can't talk about deep-sea life without marveling at deep-sea gigantism. It's a real, well-documented phenomenon where many deep-sea creatures grow to enormous proportions compared to their shallow water relatives.
Like what? Give us some examples.
Okay, well, we've got striking examples like the Japanese spider crab. It can spin an incredible 12 feet that's nearly 4 meters from claw tip to claw tip. Imagine that scuttling towards you.
12 feet wide. No, thank you.
Or the giant tube worms we find near hydrothermal vents. They grow up to 8 feet, maybe 2.5 meters in length. And remember, they do this despite lacking mouths or digestive systems entirely. They rely on those internal chemosynthetic bacteria for nutrition, basically housing an internal food factory.
8-foot worms with no mouths.
And of course the squid. There's the famous giant squid, but then there's the colossal squid. It's even larger, potentially heavier. It possesses eyes the size of dinner plates, the largest eyes in the animal kingdom. And its tentacles have not just suckers, but sharp rotating hooks that can tear through flesh and bone.
Rotating hooks. Seriously.
Seriously. These creatures aren't just big, they're almost mythological in scale.
Yeah.
Each one is a living testament to nature's ultimate problem-solving capabilities in these extreme environments.
It's truly mind-blowing. We always think of the sun as the ultimate, indispensable source of all life on Earth. But what you've just described, especially with the tube worms, completely flips that idea on its head.
It really does.
In the deep ocean, there are entire ecosystems that just, laugh at that idea. They've found a way to thrive without a single ray of sunlight, completely rewriting our understanding of life's fundamental energy source.
You've hit on one of the most revolutionary discoveries in modern biology. Perhaps the most truly alien ecosystems on Earth are those surrounding hydrothermal vents and also cold seeps. Here, life exists entirely independent of solar energy.
How? What are they using instead?
It's all thanks to chemosynthesis. That's the process where organisms derive energy from chemical reactions, or rather than sunlight. They're essentially making food from chemicals spewing out of the Earth's crust.
Making food from chemicals.
Exactly. The discovery of these ecosystems back in the late 1970s, it revolutionized biology. It demonstrated that life could exist in environments previously thought to be completely sterile, totally barren. It forced us to redefine where and how life can emerge, not just on Earth, but potentially on any planet.
Right, the implications are huge.
Hydrothermal vents, for instance, create these incredible oases of life in what is otherwise a deep-sea desert. You have superheated water, rich in chemicals like hydrogen sulfide rotten egg gas, methane, and other minerals, erupting from the seafloor at temperatures that would instantly kill most surface organisms.
Remember that 400 degrees seawater?
Yeah, the boiling hot vents.
Yet, despite these extreme conditions, these vents support some of the most productive ecosystems on Earth. The sheer amount of life, the biomass density, can rival that of tropical rainforests.
That's astounding. A barren wasteland, then a burst of superheated toxic water, and suddenly you have a rainforest-level ecosystem. How do they manage that? What's the base of the food chain?
It's all thanks to those chemosynthetic bacteria and archaea single-celled organisms. They are the primary producers, forming the base of the food chain by converting those chemicals into energy. And living off them, you find those iconic giant tube worms, Riftia pachyptilla. These worms are truly extraordinary. Again, they lack mouths, stomachs, any digestive tract at all.
Still can't quite wrap my head around that. All right. Instead, they house billions of these chemosynthetic bacteria inside their bodies, within specialized organs called trophosomes. Think of it as a dedicated internal chemical factory. The bacteria convert hydrogen sulfide into energy, and they share the nutrients with their worm hosts. It's one of nature's most successful symbiotic relationships.
And those red plumes they have?
Ah, yes. You'll recognize them by their vibrant, bright red plumes. Those are rich in hemoglobin, similar to our blood, but it's specially adapted to bind tightly to both oxygen and hydrogen sulfide, transporting these crucial ingredients efficiently to their bacterial partners living deep inside their bodies.
Wow. Okay, what else lives there?
Well, they're not alone in their adaptations. You have vent crabs that scuttle through that scalding water that would cook most other creatures instantly. Their specialized physiology allows them to survive these extreme temperature fluctuations. And then there are the Pompeii worms. These are a marvel. They live directly on the sides of the vent chimneys, the hottest known habitat for any complex animal. Their tail ends can be sitting in water as hot as 80 degrees C, that's 176 degrees Era, while their heads remain in relatively cooler 22 degrees C, 72 degrees Era, just a few inches away.
How on earth do they survive that difference?
It's incredible. They achieve this remarkable feat partly through a thick coat of bacteria living on their backs, which seems to act as insulation. And those bacteria might even provide additional nutrients through symbiosis too. It's an almost unbelievable feat of biological engineering to thrive in such a radical temperature gradient.
So it's not just the hot vents, you mentioned cold seeps too. Are they similar?
Indeed. Beyond the dramatic hydrothermal vents, we also find cold seeps. These are environments where hydrocarbons like methane and hydrogen sulfide slowly leak or seep from the seafloor rather than gushing out hot. They support different but equally alien ecosystems.
More stable, maybe?
Often, yes. Unlike the sometimes volatile, ephemeral nature of vents, cold seeps can persist for decades or even centuries, creating incredibly stable, long-lived communities. A fantastic example of life found here are the bone-eating worms from the genus Osedax. They're sometimes called zombie worms.
Bone-eating worms, what do they eat?
They specialize in consuming whale falls, the carcasses of dead whales that sink down to the ocean floor, which is a huge but very infrequent input of food.
Okay, how do they eat bone?
Astonishingly, these worms lack mouths and stomachs. Instead, they have these root-like structures that secrete acid to dissolve the bone. And then symbiotic bacteria living within these roots digest the lipids and proteins released from the bone matrix.
So they dissolve bones with acid and have bacteria inside them eat the goo.
That's pretty much it. They're essentially living bone-dissolving factories. They turn this massive, infrequent food source into the foundation for a unique, long-lasting deep-sea community. It all just highlights how versatile and unexpected life can be, constantly pushing the boundaries of what we thought was biologically possible.
Okay, my mind is officially blown by what we do know. If that's what we found in the tiny fraction we've explored, what about the vast 80% we haven't even mapped properly? What kind of unimaginable life might be lurking down there? What does this all mean for what's biologically possible? This is where the true mystery begins, isn't it? Where our imagination really has to step in.
This is truly where informed speculation becomes not just exciting, but actually a valuable tool for driving science forward. Scientists genuinely predict that millions of species remain undiscovered in the deep sea. Millions.
Millions.
And many of those might possess biological capabilities that just seem impossible by our current standards. Consider life in the deepest trenches, the Haddle zones. Down there, pressure exceeds an astonishing 1,100 times atmospheric pressure.
Even more than the 400 times we talked about earlier.
Much more. Organisms there might exist with cellular structures completely unlike those we know, perhaps using entirely different biochemistry to survive. Some scientists speculate, and this is speculation about creatures that might incorporate metallic components into their biology. creating living organisms with properties more like machines than traditional life forms.
Living machines, like with metal parts.
Potentially, yeah. Imagine a creature with a naturally occurring exoskeleton that's structured more like, say, biological steel than the chitin we see in insects or crabs. It's theoretical, but based on the pressures involved.
Who knows?
That's truly next-level alien. So the deep sea isn't just hiding unknown creatures we might recognize. It could be hiding entirely new forms of what we even consider a creature.
Exactly. Furthermore, the deep ocean's isolated basins and seamounts, remember those underwater islands? They might harbor remnants of ancient evolutionary lineages. We call them living fossils. Organisms that have remained virtually unchanged for hundreds of millions of years.
Like the coelacanth, but maybe even older or weirder. Precisely. These organisms might represent alternative evolutionary pathways, experiments that died out elsewhere on Earth but were preserved in the stable, isolated conditions of the deep sea, like biological time capsules. Discovering them could rewrite major chapters of Earth's evolutionary history.
Wow, finding echoes of ancient Earth.
And let's not forget the sensory landscape down there. We talked about bioluminescence. Imagine entire ecosystems where every organism, from the smallest microbe to the largest predator, produces light. You could have alien underwater cities illuminated entirely by living creatures, glowing forests, pulsing pathways of light.
That sounds beautiful and eerie.
And these communities might communicate through incredibly complex light patterns, creating sophisticated underwater languages. And maybe it's not just visible light. Some organisms might have evolved to produce and detect light in spectrums we can't see, like infrared or ultraviolet. Entire conversations could be happening down there, completely invisible to human eyes or current cameras.
Hidden light languages. Okay. And what about size? Could things get even bigger?
And of course, deep-sea gigantism could be amplified to an even greater degree in the truly uncharted regions. The combination of pressure, cold, and maybe lower metabolic rates might allow for the evolution of creatures far larger than anything we've discovered so far. Perhaps comparable in size to blue whales, but adapted for the crushing depths. Moving with a slow, ponderous grace, their sheer mass supported in ways we can barely comprehend.
Giants bigger than whales.
And one more thing, what about below the seafloor? We're just starting to realize there might be vast interconnected cave systems or fluid-filled pockets within the rock beneath the ocean bottom. These subsea floor environments might harbor entire ecosystems that have never been exposed to seawater, containing organisms evolved in complete isolation with unique biochemistry, potentially for billions of years. The deep ocean is the ultimate dark canvas for evolution to paint its most epic and most bizarre masterpieces.
The thought of these biological time capsules and bioluminescent cities and things living under the seafloor, it's just incredible. It really makes you wonder about the very fabric of life itself. I mean, the deep sea organisms we've already discussed push the boundaries of what we consider biologically possible. But what about capabilities that seem to almost violate the laws of physics as we understand them? What could be even more extreme out there, just waiting for us to imagine it?
It's an incredible thought experiment, right?
Yeah.
Pushing the limits of our biological understanding to the very edge.
Yeah.
And based on the truly extreme conditions that might exist in the deepest, most unexplored pockets, we can theorize some truly astonishing, almost fantastical adaptations. Though, again, this is getting into the realm of informed hypothesis.
Okay, let's hear them.
For instance, organisms living near the very deepest trenches, where pressure is just immense and the environment incredibly stable over geological timescales. They might have evolved crystalline structures within their bodies to withstand that crushing pressure, essentially becoming living minerals.
Living minerals. What would that even look like or function like? How would that work?
Well, maybe these creatures could incorporate silicon or metals or other inorganic compounds directly into their biological structures, creating these hybrid organic-inorganic organisms. Their very physical makeup would be unlike anything we currently define as life, really blurring the lines between what is animate and inanimate. They might grow very, very slowly, like crystals themselves, and be incredibly durable.
Blurring the lines between rock and animal. Okay, what else?
Then there's the possibility, perhaps driven by the extreme cold and pressure, of superconducting biology.
Superconducting, like in physics, with zero electrical resistance.
Exactly. The conditions might allow for organisms with biological components that act as superconductors, enabling them to transmit electrical signals like nerve impulses with perfect efficiency, no energy loss.
What would be the advantage of that?
Imagine the implications. Such creatures might possess nervous systems that operate closer to quantum mechanical levels, Maybe they could leverage the strange properties of the subatomic world particles existing in multiple places at once, things like that, to process information with incredible speed and efficiency, far exceeding the capabilities of any known organism.
So their brains could literally be operating on principles of quantum physics. That's almost beyond science fiction. And what about time? Could they manipulate time itself in some biological way, maybe live incredibly long?
It's an interesting concept to explore. Some deep-sea organisms, perhaps facing very infrequent food falls or environmental shifts, might have evolved the ability to enter states of suspended animation. Not just hibernation, but true suspended animation lasting decades, maybe even centuries.
Waiting out the bad times.
Exactly. Waiting out periods of environmental stress or food scarcity. These creatures might essentially stop aging during these dormant periods, achieving forms of biological immortality unknown in surface organisms. They could effectively press pause on their lifespan, only to resume activity when conditions become favorable again. It's not just about slowing down, it's about potentially a radical re-engineering of the aging process itself.
Biological immortality. Wow. Anything else?
And finally, perhaps linked to the cold, consider supercooled life. We know high pressure can change the freezing point of water. It might enable organisms to maintain liquid water within their cells at temperatures well below freezing, allowing life to exist in environments previously thought simply too cold for biological processes to occur.
Liquid water below freezing.
Under pressure, yes. These supercooled organisms might have metabolisms that operate at extremely, almost imperceptibly slow rates.
Yeah.
Living lifespans measured perhaps in millennia, while still maintaining active biological processes. This isn't just survival, it's redefining the very pace and duration of life itself, pushing the boundaries of what a metabolism can even be.
Wow. Those are concepts that truly expand our minds. Living minerals, quantum brains, biological immortality.
Yeah.
It's incredible. But, while the giant squid and the glowing fish grab the headlines, maybe the real alien frontier, the truly transformative discoveries, might be hiding in plain sight. On a scale we often overlook, microscopic.
You're absolutely right. I think that's a crucial point. While the megafaunas are captivating, deep-sea sediments, the water column, even the rocks beneath contain these vast communities of microorganisms, bacteria, archaea, maybe even stranger things.
Yeah.
They might represent entirely new domains of life. Their biochemistry, their cellular structures could be unlike anything currently known to science. These are the true pioneers of extreme environment, the fundamental building blocks of novel biology.
Entirely new domains of life, like bigger categories than bacteria or animals?
It's possible. The genetic diversity down there is astronomical, and much of it doesn't fit neatly into our existing classifications. Consider, for example, radiotrophic organisms. This is a hypothesis gaining some traction. Microorganisms existing perhaps in the deepest ocean sediments, or even within the oceanic crust, that derive energy directly from radioactive decay, using the natural radioactivity in the rocks and sediment as their primary energy source.
Life-eating radiation instead of sunlight or chemicals.
Exactly. These radiotrophic organisms might represent an entirely new category of life, completely independent of both sunlight and the traditional chemical energy sources we find at vents and seeps. It completely redefines the energy landscape for life, showing it can literally feed on the fundamental physics of the environment.
That's incredible. And what about their cellular structure itself? Does the immense pressure affect that on a microscopic level too?
Oh, absolutely. The high-pressure environment must impose incredible constraints, but also opportunities. It might allow for microorganisms with cellular structures simply impossible at surface pressures. They could have developed unique methods of genetic replication, protein synthesis, cellular division, all perfectly adapted to the immense forces acting upon them. Their very cellular machinery, the nuts and bolts of their existence, would likely be alien to us, maybe using different molecular scaffolding or osmotic strategies just to maintain integrity.
So pressure could lead to fundamentally different types of cells.
It could. And here's a truly mind-bending idea linking back to the quantum discussion. Quantum biological microorganisms. What if some deep-sea microorganisms possess the ability to directly manipulate quantum mechanical processes, using quantum effects like tunneling or entanglement to enhance their metabolism, maybe for navigation or even communication?
How would that even work biologically?
We barely know. But these hypothetical quantum biological organisms might represent a bridge between classical biology and quantum physics, demonstrating biological applications of quantum mechanics that we're only just beginning to understand even in our most advanced technology. It suggests life could be harnessing fundamental physics in ways we currently only imagine in labs.
Okay, that's way out there, but fascinating. One more microbial idea.
One more. Let's speculate about microbial superorganisms. What if some deep-sea microbes don't just exist as individuals, but in a state of, well, collective consciousness, forming vast networks of interconnected organisms that function essentially as a single massive entity,
Like a slime mold, but way bigger and maybe smarter.
potentially orders of magnitude bigger and more complex? These microbial superorganisms could span entire ocean basins, maybe processing information and making collective decisions on unprecedented scales. Imagine a living, perhaps even thinking, carpet of microbes covering kilometers of seafloor, sharing intelligence and resources through biochemical signals. The implications for understanding consciousness and distributed intelligence are profound. It suggests an alien form of intelligence could be right beneath our feet, operating on principles we don't remotely grasp.
These ideas really challenge our very definitions of life and intelligence. It makes you realize this deep dive isn't just about what lives on the seafloor, is it? It's about the entire water column, connecting the surface and the deep in ways we're just beginning to grasp. We're talking about incredibly complex, almost interdimensional ecosystems where life moves and adapts across vast vertical distances.
Exactly. What's fascinating here is the sheer dynamism of these ecosystems. It extends far beyond just a static seafloor. We're talking about the diel vertical migration. By biomass, this is actually the largest migration on Earth every single day.
The largest migration on Earth happens every day in the ocean. How does that work?
Billions, maybe trillions of organisms from tiny zooplankton to larger fish and squid move vertically through the water column. They travel hundreds, sometimes even thousands of meters up towards the surface at night to feed in the richer waters, and then they retreat back down to the safety of the dark depths during the day to avoid predators. This creates these incredible dynamic connections between surface and deep-sea environments that we're only starting to really map and understand.
That's an incredible daily commute. What kind of adaptations would that require? I mean, moving through radically different pressure zones, light levels, and temperatures every single day.
Exactly. The physiological challenges are immense. Many of these migrating organisms remain unknown to science or poorly understood. They represent potentially alien life forms that have to traverse multiple extreme environmental gradients: pressure, temperature, light during their daily journeys. Imagine the physiological adaptations required to handle such dramatic shifts every 24 hours without literally exploding or freezing or being blinded. It suggests an extreme flexibility in their biological systems we barely comprehend.
So there could be whole communities just moving up and down constantly.
Yes, and linked to that, there's also the mysterious deep scattering layer. This is a phenomenon detected by sonar for decades. It appears as a false bottom to the ocean on sonar screens, often mistaken for the actual seafloor. It moves up and down with the daily migration cycle.
What is it?
Well, that's the mystery. It's poorly understood biologically, but it clearly represents vast communities of organisms that exist at specific depths during different times of day. But what kind of organisms? Some speculate these communities might consist of creatures so different, maybe gelatinous or with weird acoustic properties, that they don't register properly on traditional sampling nets or cameras. They could be entirely new forms of life with physical properties that confound our current detection methods, perhaps even evolved specifically to avoid detection. They remain largely invisible to direct observation.
A layer of hidden life moving daily. Wow. And how do these connect across the ocean horizontally?
Well, if we connect this back to the bigger picture, those seamount chains we discussed earlier, they might serve as underwater highways for deep-sea species, creating these corridors for genetic exchange across vast ocean basins.
Stepping stones, like you said.
Exactly. The organisms that travel these routes might be highly specialized long-distance migrants, adapted for crossing huge expanses with minimal energy. They could possess navigation abilities that operate on scales and through mechanisms we can't yet comprehend, maybe utilizing subtle shifts in currents, the Earth's magnetic field, or faint chemical cues carried across thousands of miles of ocean to find their way from one seamount island to the next. These interconnections show that the deep ocean isn't just a series of isolated pockets. It's a vast, interconnected, and highly dynamic living system that's constantly in motion, vertically and horizontally.
It truly paints a picture of a living, breathing, almost pulsing alien world right beneath us. Okay, given how incredible and vital this all sounds, you, the listener, might be asking, why haven't we seen more? Why is so much still a mystery?
Hmm.
It's clearly not for lack of trying, right? It must be because this is just one of the toughest places on Earth, maybe even the toughest to explore. It presents these immense technological and logistical challenges that, I don't know, make space exploration look almost easy by comparison sometimes.
That's a crucial point, and it often surprises people. You're right. The primary reason vast areas of the deep ocean remain unexplored is indeed the immense technological challenge of just operating in such extreme environments. Building vehicles, whether manned submersibles or remotely operated vehicles, ROVs, that can withstand that crushing pressure, remember, up to 1,100 times atmospheric pressure in the deepest trenches, while also carrying sophisticated scientific instruments, cameras, lights, manipulators, and sometimes life support for humans. It requires engineering solutions at the absolute limits of current technology. We are literally building deep space capsules, but designed for immense external pressure instead of vacuum.
And I imagine this kind of cutting-edge, bespoke technology doesn't come cheap. That must be a factor.
Oh, far from it. The cost is another huge factor. Deep sea exploration genuinely rivals that of space exploration in terms of cost per hour or cost per mission. This severely limits the number of missions that can be funded and undertaken to the ocean depths. We're talking incredibly expensive ships to support the operations, highly specialized crews both on the ship and piloting the vehicles, and massive logistical planning for every single dive. Budgets are finite, and unfortunately, the deep ocean often competes with more publicly visible or perhaps commercially driven scientific endeavors.
Okay, so it's hard to build the tech, and it's expensive to use it. What about time? Can we stay down there long?
That's another major bottleneck. Severe time constraints. Current deep-sea vehicles, especially the human-occupied ones, can typically only remain on the bottom for a matter of hours, maybe a day or two, at the absolute maximum for some robotic systems. This severely limits the time available for observation, exploration, and sample collection in any one spot.
Just brief visit.
Exactly. The vast majority of deep-sea research relies on these brief visits that capture only snapshots of what are often very dynamic ecosystems. This means many deep-sea organisms might be active only during specific conditions or certain times, or react to events like food falls that researchers have simply never witnessed because they weren't there at the right moment. They become effectively invisible to our current methods, like trying to understand a bustling city from a single, fleeting photograph taken at midnight.
That's a huge limitation. So even if we find something amazing, studying it properly can be nearly impossible, right? Because we can't bring them back easily.
Exactly. We also face the fundamental challenge of specimen mortality. Many, perhaps most deep-sea creatures die immediately or very quickly when brought to the surface. The change in pressure decompression is catastrophic for them.
Like the bends for divers, but way worse.
Way, way worse. Their bodies are so perfectly adapted to the high-pressure environment that the rapid decrease in pressure causes their internal structures, their cells, maybe dissolved gases in their tissues, to simply burst or malfunction. Their proteins might denature, just like we discussed earlier, with surface pressure being lethal to them.
Yep.
This makes it incredibly difficult, often impossible, to study their behavior, their physiology, their life cycles under controlled laboratory conditions. We can't keep them alive at surface pressure.
So we can't really study them alive properly.
For many species, no. This means entire aspects of deep-sea biology remain unknown, simply because we can't bring these organisms into our laboratories and watch them live normally. We often only ever see them in a dying or compromised state, or just as preserved specimens. And finally, even trying to study them from afar is hard. Remote sensing technologies that work well in other environments like satellite imaging, radar, even some forms of sonar or light-based imaging often fail or perform poorly in the deep ocean. Sound waves behave differently under pressure, radio signals don't penetrate wire well at all, and light gets absorbed very quickly, limiting visual range. This forces researchers to rely heavily on getting vehicles down there for direct observation and physical sampling, which, as we've said, dramatically increases the cost and complexity. It's a truly formidable frontier to conquer, demanding immense patience, resources, and ingenuity.
That really contextualizes why we know so little, despite its immense scientific value and just sheer coolness factor.
Okay, so thinking about this hidden world, what's happening to these alien ecosystems, even the ones we barely know exist, as our planet undergoes significant changes, climate change, pollution? Are we impacting realms we haven't even fully explored or understood yet? It's kind of a sobering thought that our actions on the surface could be reaching down and affecting the deepest, most isolated parts of our planet.
This raises an important question, connecting the known impacts to the vast unknown. And it's one of the most pressing concerns in oceanography today. The short answer is almost certainly yes. As climate change alters ocean conditions, globally warming waters, changing chemistry, shifting currents, it's highly likely affecting deep-sea environments in ways we don't yet fully understand, partly because we lack baseline data for so much of it.
How do surface changes reach the deep? Well, these changes in surface temperature, ocean chemistry from absorbing CO2, and large-scale circulation patterns are not just impacting the top layers. They can cascade down, sometimes slowly, sometimes surprisingly quickly, to the abyssal plains and even the deepest trenches. They impact the delivery of oxygen, the flow of food particles from above, and the fundamental chemistry of the water, affecting ecosystems that may have evolved in incredibly stable conditions for millennia.
Okay, like what specific impacts are scientists worried about?
Well, one major concern is ocean acidification. This is caused by increased atmospheric CO2 dissolving into the oceans, making the water more acidic. This is particularly pronounced in colder deep waters, which can absorb more CO2. This change in pH might be acting as a strong selective pressure, favoring organisms with novel shell building or pH regulation capabilities while harming others, like corals or shelled mollusks.
So it could wipe some things out, but maybe promote others.
Potentially. Deep-sea creatures might be forced to evolve new forms of biomineralization. That's the process of forming mineral structures like shells or skeletons that can function in increasingly acidic conditions. This could potentially create organisms with shell structures unlike anything currently known. So, yes, it's not just about species dying off. It's about potentially driving entirely new, perhaps unforeseen, evolutionary pathways in response to our global impact.
So we could be inadvertently accelerating the evolution of new kinds of alien life down there by stressing the system.
Exactly. It's a complex outcome. Also, changing deep water circulation patterns, the way water moves around the globe in the deep ocean, are predicted as the climate warms. These currents are crucial for distributing oxygen and nutrients. Changes could lead to expanding oxygen minimum zones, or they might isolate previously connected populations of deep-sea organisms, cutting off gene flow between different basins or seamounts.
What would that isolation do?
Well, this accelerated isolation could lead to rapid speciation, the formation of new species, as these separated populations evolve independently. So you might actually get more diversity in some ways, creating new endemic species adapted to slightly different local conditions. But this could come at the cost of existing, perhaps more widespread, deep-sea biodiversity that cannot adapt quickly enough to the changing connections or conditions.
More species, but maybe losing others we never knew.
Precisely. And furthermore, rising ocean temperatures themselves, even if the increase seems small compared to surface warming, could be significant in the normally stable deep sea. This warming could be pushing some deep-sea organisms that are very sensitive to temperature to even greater depths, forcing them into environments with even more extreme pressure in search of their optimal colder temperature range.
Pushing them deeper into the unknown.
Right. And this additional environmental pressure might, again, accelerate the evolution of even more alien adaptations, creating creatures adapted to conditions previously thought uninhabitable, or alternatively, it could simply drive others to extinction before we even discover them if they can't migrate or adapt. It's a profound thought. We might be inadvertently accelerating the creation of new forms of alien life on Earth through our global environmental changes, even as we struggle to understand the incredible life that's already there and potentially losing some of it unseen.
That's a truly thought-provoking and, yeah, slightly unsettling consequence. But okay, let's shift perspective a bit. Here's where it gets really interesting for anyone fascinated by the universe beyond Earth. What if the aliens were searching for, sending probes to Mars, listening with radio telescopes? What if the most relevant aliens, in a way, aren't light years away in the stars, but right here under our waves? What can Earth's deep oceans tell us about the search for life elsewhere?
This is truly astrobiology on our doorstep, and it's a profound and incredibly important connection. Many astrobiologists, scientists who study the potential for life beyond Earth, intensely study deep-sea organisms precisely for this reason. Because the conditions in Earth's deep ocean, the high pressure, the low temperatures, the perpetual darkness, the exotic chemistry around vents and seeps, might be remarkably similar to conditions we suspect exist in the subsurface oceans of icy moons in our own solar system.
Like Europa or Enceladus.
Exactly. Europa, an icy moon of Jupiter, and Enceladus, an icy moon of Saturn. Both are thought to harbor vast liquid water oceans beneath their icy shells. And the energy sources and chemistry in those hidden oceans might resemble our deep-sea hydrothermal vent systems more than anything else we know. Our deep sea is a direct analog, our best natural laboratory, for understanding what might be possible there.
And the chemosynthesis angle is key there, right?
Absolutely critical. The chemosynthetic ecosystems of our deep ocean are powerful proof of concept. They demonstrate unequivocally that life can exist and even thrive complexity, entirely independent of stellar energy of sunlight. This strongly suggests that similar ecosystems, powered by geothermal heat and chemical reactions from the moon's interior, might exist in the dark, sunless oceans beneath the thick ice shells of these outer solar system moons. It means you don't need a sunlit surface to have a potentially vibrant, complex ecosystem.
So these deep-sea vents and seeps aren't just fascinating on their own. They're essentially terrestrial laboratories for developing hypotheses about alien life.
Exactly. They show us what's possible. And the extreme adaptations of deep-sea organisms, tolerance to pressure, cold, darkness, weird chemistry, further show that life can evolve to survive in conditions far more harsh and unfamiliar than those on the surface of most planets we think of. Plus, some researchers even propose that life on Earth might have originated in deep-sea hydrothermal vents billions of years ago.
The origin of life itself, down there.
It's a leading hypothesis. If true, these environments are not just analogs for alien life, but potential windows into the earliest forms of life on our own planet. Studying the most ancient and alien organisms in our own oceans might reveal fundamental principles about how life emerges and evolves under extreme conditions, principles that could apply universally across the cosmos. So really, the discovery of each new deep-sea organism, each new extreme adaptation, profoundly expands our definition of the possible. It suggests that life in the universe might be far more diverse, far more adaptable, and frankly, far stranger than we currently imagine. The aliens living in Earth's oceans might be preparing us, expanding our minds for the even stranger life forms we might eventually encounter on other worlds. They're pushing the boundaries of what we can even conceive of as life.
It's really inspiring to think that the exploration right here on Earth is directly informing our search way out there in space. Okay, but as we discussed, exploring the deep is hard. But it's not all doom and gloom and technological limitations. What exciting new tools and advancements are on the horizon? What's coming that will help us finally unveil these alien oceans and their secrets? The future of deep-sea exploration must be looking brighter than ever, right?
Oh, absolutely. You're right to be optimistic. Despite the challenges, emerging technologies are really poised to revolutionize deep-sea exploration and unlock its mysteries in ways we can only dream of just a few decades ago. It's a very exciting time to be in the field. One of the most promising advancements is in autonomous underwater vehicles, or AUVs. These are essentially advanced, intelligent robots that can operate without a tether to the surface ship.
Untethered robots.
Exactly. Powered by increasingly sophisticated, long-duration batteries, or maybe even small, safe nuclear reactors for very long missions in the future, AUVs might soon be able to spend weeks, maybe even months, exploring the deep sea completely on their own without direct human intervention during the mission.
Wow, months underwater, what could they do?
These robotic explorers could map vast areas of seafloor with unprecedented detail using advanced sonar and optical systems. They could collect incredible amounts of environmental data, temperature, salinity, chemistry, and they could use cameras and other sensors to observe deep-sea life over extended periods, giving us continuous insights into behavior and ecosystem dynamics rather than those fleeting glimpses we get now.
So instead of just a few hours of observation here and there, we could get months of continuous data collected autonomously. That's a huge step forward.
A monumental one.
Yeah.
And alongside that, advanced material science is also making huge strides. Researchers are developing new composite materials, ceramics, and alloys that can withstand extreme pressure while remaining relatively lightweight.
Why is lightweight important?
Well, it's critical for enabling the construction of larger deep-sea vehicles, both manned and robotic, that can carry more sophisticated scientific equipment, heavier battery systems for longer missions, or more sample storage. These next-generation vehicles might be able to collect larger or more delicate specimens using new techniques, operate more complex sensor suites, and maybe even conduct more intricate experiments directly on the seafloor, really expanding our ability to interact with and study these environments in situ, right where they are.
Better subs, better robots. What about finding things we can't even see?
That's where genetic sequencing, particularly through environmental DNA or eDNA, comes in. This is another potential game changer. The technology is becoming so advanced, so sensitive, and so affordable that it might soon be possible to sequence the DNA of entire deep-sea ecosystems directly from samples of water or sediment.
How does that work? Just scoop up water?
Essentially, yes. Organisms constantly shed DNA into their environment, skin cells, waste products, etc. This eDNA approach allows us to collect that water or sediment, extract the DNA fragments floating within it, and sequence them. This can uncover vast communities of unknown organisms from bacteria and archaea right up to large, elusive animals without ever physically seeing or capturing them. It reveals life that might be too rare, too fragile, or too deep to capture with traditional nets or cameras.
That's almost like taking a biological fingerprint of an entire ecosystem just from the water. You don't even need to see the creature to know it was there.
Right.
What about making sense of all this new data flooding in?
That's where artificial intelligence and machine learning, AML, are becoming indispensable. These powerful computational tools are being applied to the analysis of the massive datasets generated by deep-sea exploration, especially imagery and acoustic data. We already have vast archives, petabytes, of deep-sea video footage and sonar readings that have never been thoroughly analyzed simply because of the sheer volume. There aren't enough human eyes or hours to go through it all.
So AI can watch the videos for us.
In a sense, yes. AI and machine learning algorithms can be trained to rapidly process this data, automatically identify known species, flag unknown or unusual organisms, detect specific behaviors or patterns, and identify geological features far faster and potentially more consistently than humans can. In fact, AI might even discover completely new species or phenomena hiding in plain sight within existing data archives, unlocking discoveries from research we've already conducted but haven't fully processed yet. It's an incredibly exciting time for deep-sea science, genuinely promising a surge of new discoveries in the coming decades.
That really does sound like a revolution is underway. So let's try and wrap this up. What does this all mean for us? Our deep dive today has truly taken us to what might be the largest frontier for discovering truly alien life, not in space, but right here, on our own planet, right here at home. We've explored the sheer, mind-boggling scale of the unknown, the incredible physics of survival under pressure and in darkness, and the utterly bizarre creatures that call these crushing depths home. The vast majority of Earth's deep ocean remains unexplored, which strongly suggests that the most alien creatures on our planet probably haven't even been discovered yet. From organisms that thrive under pressure that would crush a tank, to creatures that literally eat chemicals in perpetual darkness, the deep ocean hosts life forms as strange, as wondrous as anything science fiction could imagine. And as we develop these amazing new technologies you mentioned, the AUVs, the eDNA, the AI, we're likely to discover creatures that will fundamentally expand our definition of life itself. Maybe those living crystals or creatures with quantum mechanical nervous systems or organisms that manipulate time through their biology. The impossible seems to become commonplace in the alien oceans right beneath our feet.
It really forces us to reconsider our place and our perspective. And this raises an important question, I think, for you, the listener, to ponder. When we so eagerly look for life beyond Earth, when we invest so much hope and resource into sending probes to distant moons and scanning the skies for faint signals from exoplanets, are we perhaps overlooking the incredible fundamental lessons and just the sheer breathtaking wonder that is thriving just miles beneath us in our own oceans? The deep ocean shows us, unequivocally, that life is far more creative, far more adaptable, and far, far stranger than we ever imagined possible based on our surface world experience. It truly makes you wonder, if these aliens are thriving just miles beneath us in conditions we long thought were utterly uninhabitable, what else could be out there? In the cosmos, sure, but maybe even in other unexplored corners of our own world, deep caves, the upper atmosphere, beneath the ice sheets, places we have yet to truly see. So what stands out to you from this journey into Earth's most alien frontier? And what questions does it spark for your own curiosity about the boundless and perhaps truly limitless possibilities of life?